In this video, I'll be demoing a compiler I wrote for a custom programming language I'm calling Functional Language 1. I thought it would be interesting to try and create a language that has as few features as possible, while providing as much power and expressiveness as possible, with terse and type-safe code. With those goals in mind, I based FL1 heavily on the Haskell programming language, but I left out quite a few Haskell features and mixed in a few features from other languages as well. I'm going to be referring to the compiler as a transpiler, as it generates JavaScript as its output instead of assembly code. The transpiler has a REPL interface, REPL standing for Read, Evaluate, Print loop. In it, the user can load symbols from source files and execute expressions utilizing those symbols. For example, I could enter a simple arithmetic expression, and it'll evaluate it and print the output, as well as the resulting type. The user can also define new single-line functions, which are then added to the list of loaded symbols. So I could define a function called add, takes a and b as parameters, and adds them together. And then I can call add immediately on arguments, and it evaluates. The language also supports a partial function application. This means that if you only supply some of a function's arguments, it will return a new function that takes the remaining arguments as input. So if I define a function called increment that equals add 1, I can execute increment on a number, for example 7, and it'll evaluate to 8. You can also create lists, so we can create a list of integers here. And it interprets it as a list of integers. Notice that we didn't need to specify any types, those are inferred. You cannot, however, have lists with multiple mixed types. You'll get a compiler error in that case. One useful list operation is the map function. Map takes a unary function on t and a list of t and returns a new list of t. So for example, we can map our increment function over some integers, and it'll return a list where every integer has been incremented by 1. We can also filter lists. So let's say we wanted to get all the even whole numbers from 1 to 100. We could define a function called isEven that determines if an integer is even. And then we can filter a list with that even function. So filter isEven, and I'm going to use the range operator to get a list of numbers from 1 to 100. And that evaluates to a list containing every even number from 1 to 100. If we want to implement multi-line functions, we'll need to write them in a source file and load them in. Here are a few examples that showcase other types of expressions you can write. First, we have a sign function that utilizes simple if-then-else expressions to determine the sign of an integer. Next, we have a function that finds the length of a linked list recursively. It uses pattern matching to determine whether we're looking at a list node or the end of the list. If we're looking at a node, it'll extract a tail and return its length plus 1. I borrowed this syntax from a book called Pattern Calculus, which is all about pattern matching. And I like the syntax because the data you're matching against is actually from an implicit parameter on the function. So this syntax here is equivalent to having an explicit parameter and matching on it. But it's a little more terse in that it's an implicit parameter. The final function here is an example of a closure expression denoted by the curly brace. Closures let us write imperative code where every line will be executed sequentially and the last line will be returned. The function prompts the user for their name and binds the result to a variable called name, and then prints name out in a greeting. So if we invoke the greet function, you'll see that it prompts for a name, so I'll enter my name, and it greets me. And here you'll see the return type, or the return value is an empty tuple. I decided to represent void with empty tuples in this language, since every function has to return some value. Okay, finally, FL1 supports a kind of type called type classes, which are similar to interfaces in object-oriented language, in that they define a set of functions that subtypes must implement. However, type classes allow polymorphism on every parameter of these functions, as well as on their return types. For instance, let's look at the numeric type class, which declares the arithmetic operators plus, minus, times, and divide. So if we look at plus, we'll see its type. It's basically saying here, for any numeric type t, it'll take two t's as input and return t as well. Integers and real numbers both are numeric types and both implement plus. The integer plus operator requires integers as inputs and has an output type of integer as well. If we try to add data of different types, we'll get a compiler error. So if I add the integer, the real number, we'll get a compiler error. However, thanks to the way type classes work, we can still write generic functions using the plus operator. So I could define a function that sums a list of numbers. And we can execute it on a list of integers, and that works. And we can execute it on a list of real numbers as well. And you'll see that that worked as well. Next, we'll look at how the transpiler pipeline processes FL1 source code. First, the parser takes the source code and breaks it up into tokens delimited by white space. Then it creates a data structure called an abstract syntax tree to represent the code using key symbols like equal signs, parentheses, and indents as context for what the surrounding code means. Next, the AST is passed to the analyzer, which is by far the most complex stage. It performs type inference and verifies that other semantic rules are followed. I use the Hindley-Milner type inference algorithm as it provides complete type safety without the user having to annotate any types at all in their functions, leading to very terse and readable code. It works by traversing the AST, looking at each node, assigning it a type variable if it's not already known, and creating constraints between the node's type and the type of its children based on a few simple rules. These constraints from the inference algorithm can then be solved, and if there are no contradictions, the types of each node are now known. One problem that I didn't anticipate was that in order to allow mutual recursion between functions, without any special syntax, I had to perform type inference on all the functions in a file simultaneously. However, this was problematic as the functions that weren't even involved in the mutual recursion were getting assigned overly constrained types. For instance, the algorithm would determine the input type of the concat operator as list of int instead of list of any, just based on other functions in the file with it. What I ended up doing was coming up with a batching algorithm that looks at calls made in each function, batches functions together if they have mutual recursion, like G and H here, and then it would perform type inference on each batch separately to ensure correct type assignment without over-constraining any types. After that, if analysis succeeds, the AST will get passed to the generator, which converts the ASTs into JavaScript and emits it into a single output file. JS was a nice output language as it provides things like garbage collection for free, and it's dynamically typed, so I didn't have to worry about generating any type annotations. Here's an example of what the output JavaScript would look like for a simple function like this. Finally, the transpiler will invoke Node.js, a server-side JavaScript runtime, to execute the output JS file and report the result. That's it for the demo. Thanks for watching.